So today we'll talk about a proposal for implementing RAG at a federal government client. So one of the use cases is to identify security hazards in the public. There is a huge amount of video data coming in from various locations, from building tops and entrances to stores and so on. So taking that image and using some AI algorithm, potentially from NVIDIA, to detect what's happening. And conventional technology uses that. So today, with the current technology, we don't need huge amounts of data. There are different standard activation patterns like raising a hand, raising a leg, looking up, looking down, crouching, walking, whatever the case might be. And based on that, we have the basic actions learned in the AI system and rules for recognizing behavior, especially some kind of negative behavior. And then these rules or combination of these rules forms the basics for some kind of action that is suspect. So typical use case requires something like a fast response time in criminal activity detection, less than 1 second, latency across the data and RAG pipelines. It needs to augment information from the public domain, from police databases and so on. And it complements textual credit card usage, geographical data, past criminal data, etc. So multimodal RAG provides signals in most dimensions. And the emerging agentic RAG combines the answers from multiple domains. So that is one way to address this problem. Now we have various other models from Hugging Face like LaLava that can be used to augment the information. So here's a graphic about how retrieval augmented generation works. You have data collections, information extraction, chunking, embedding, index plus search retrieval, and LLMs. So what are the data sources and how should we commission or acquire these extra data sets? How do we extract the information? What tools and techniques do we use? How do we chunk the data? If you take a large piece of data, how do you divide into small manageable parts? And then you embed the data, which embedding model works better? So basically we take this text, we chunk them, and then we take a chunk and embed the words in that chunk in form of a vector so that you can conduct vector searches for semantic similarity between two different textual patterns. Then you have an index search retrieval. Should we use a vector database or an existing system like PostgreSQL? Which vector database should we use? What kind of search and retrieval algorithms work best? Like a nearest neighbor algorithm is pretty common in this space. And then should we use open source, proprietary, or both? So what is RAG? You have an enterprise knowledge database, you pre-process the documents are fed to the embedding model, the document embeddings then come out into vector database, and that is the preparatory step. And then when a user does a query retrieval, then through a chatbot, then the user query goes into the embedding model. Now you take the query and the embedded query, send it to the vector database. So then you have a user's prompt plus query plus retrieved content that is fed to an LLM. And in this case, ideally the LLM is prompt tuned to a particular domain, and that standard stream text response, the generated response, comes back to chatbot and communicates back to the user. So in order to accomplish that, this is how the pipeline typically works. Questions come in, and then embedding generation service works on it. You create a vector, that little green bar with a red dots, that's the vector. And then you store a number of these vectors in the vector database. And from there, you use nearest neighbor to find out. For example, the cat sat on a, and then there should be a pattern which says cat sat on a wall, cat sat on a ledge. So it does that similarity search and pulls those related documents. And then Once again, based on the prompt context, some of those documents are relevant. So that gets set into the LLM. So LLM has its own set of corpus of data, and this context is now getting fed to the LLM, so it enriches that corpus of data with corporate specific, domain specific information, and then the LLM uses its standard mechanism, feed forward networks, BERT algorithms to finally generate the answer. So we have different options, right? So the question comes in, the question is decomposed into multiple sub questions. They get sent through a router. And are these questions relevant to the particular index on hand? If it is, then you do a hybrid search, which is a combination of lexical search using the NVIDIA NeMo retriever embeddings, and then the answer is now sent it to retriever re-ranking. So then you re-rank these different components of the query. Then you grade the documents. Once you re-rank these documents based on what is relevant to that query, you grade the documents, disregard any irrelevant documents. With the relevant documents, you generate answers. Then you pass it by a different program called a hallucination checker. And there are some good hallucination checkers in the public domain. And then final answer comes out. So you could use semantic search or graph retrieval algorithms. So everything ultimately is some kind of a graph with relationships. And then the hyperparameters for this model are the size of the chunk, it could be bigger or smaller, number of documents written based on that particular search. Second option, the top part is all the same. In the bottom part, if the questions are not there in the index, then you perform a web search, retrieve the documents, and present them. The third option, the top portion is exactly the same. In the bottom part, if the questions are not in the local index, then you rewrite the question, and then that gets passed on to the query decompose phase. So by rewriting the question, you are coaching the LLM to come up with a more relevant and restricted answer. So here are some of the challenges that I faced. Untested open source models. The open source models don't work on first attempt. So although you'll hear a lot of press around some models, but it requires to be more customization and further tuning in order to make them work. Data quality and prep. The performance of these systems depends on the quality, accuracy, and prep. So poor data quality can lead to inaccurate or misleading outputs. Next is latency. Processing large volumes of docs presents a challenge. So response times could be slower. So balancing efficiency and effectiveness needs to be worked on. Computational resources, they require substantial computational power, especially with these large language models and extensive corporate knowledge databases. And then integration of external knowledge. When RAG improves accuracy by incorporating external information, it reasons over extended context, which is not readily available today. So that becomes challenging. So limited context does a good job, but extended context, there is some amount of confusion and hallucination. So if you look at real-time object detection, you implement RAG for fast and accurate object detection. And sometimes that poses challenges, especially if you want a quick response. What are the components? So you have a query decomposer, you have a router, you have a retriever, you have a grader that checks if the passages or chunks are relevant to the question on hand. Then finally, hallucination checker to see if each chunk data is relevant. And then there's also post-generation validation, verification, since models are not explicitly trained to follow facts from passages. So here is a different view. Submitting a query goes to the application, it forwards the request to a backend. Backend then uses some technology like Elasticsearch to retrieve the document. Then it submits the document to the re-ranking algorithm. Re-ranking algorithm returns the most relevant document, and the generated answer is now presented back to the application and to the end user. So before the answer is actually sent to the end user, one option is to send it to an LLM, passing the document as a context, and then LLM like OpenAI or WatsonX or Google send the answer back, and that generated answer is now put back into the app, and that gets sent to the end user. So some initial ROI analysis, typically about 75,000 to 100,000 to set up and customize. Then there is the annual licensing fee that would pay to Microsoft or OpenAI or IBM. Then there is ongoing support and maintenance, 15% of the licensing fee. Then there is the ROI, 20 to 30% reduction in time spent on data retrieval, about 15 to 25% in decision making accuracy based on the information, because it's now very relevant to the corporation as opposed to being a general model for the entire world. And there is about 10 to 20% increase in operational efficiency, given that number of steps can be collapsed into a few steps with API calls to these LLMs and surfacing the answer via a chatbot to the end user. So cost savings, depending upon the use case, about 150 to 250,000 annually for small to mid-size use cases. If you are looking at company-wide use cases, the savings could run into millions of dollars. You could potentially see a revenue increase of 5 to 10% through improved decision making and faster innovation. So typically the break-even point is about 12 to 18 months based on what you spend and what you see. So here is a different view, a little bit more information here. So some of the problems, technical problems, limited context window. Large language models have limited context window, and therefore you have to chunk the documents. But once you chunk the documents, again the overall context is lost because now decision making happens on individual chunks. So there could be noise in the search results, which means they are not always perfect. So because of this, we have this concept of re-ranking. So what you do is you fetch the top and 25 related chunks using some search algorithm and smaller models. And then of the top 25 related chunks, then you use a model to re-rank the top n chunks, selecting the top k most relevant ones out of the top n. So what it helps is you can then scale for massive domains like 100,000 documents, increasing the likelihood of relevant results. Efficiency, smaller models with efficient search algorithms, they do a better job retrieving a large number of relevant chunks. So some of the benefits of this process of re-ranking, you increase the precision, relevance of the top k chunks, because now you're doing a high recall search for top n out of the overall corpus of data, the universe of data. And then you are efficiently using the resources. So smaller models handle initial searches, reducing the computational overhead. And then finally, flexibility. It allows for adjusting trade-offs between recall and precision. So that's what I wanted to cover. I have some material in the appendix, but I won't go into that. So any questions?